Modern civilization is tethered to a network of infrastructure floating a few hundred miles above our heads. This network lives in low Earth orbit, or LEO, the region of space below 2,000 kilometers where most artificial satellites operate. Global financial transactions, GPS navigation, and climate monitoring all depend on these machines remaining intact. In the year 2189, a man named Elias Vey works in a buried fault in the Andes. He is an archivist of a time when the sky is permanently closed, studying the records of the era when we could still reach the stars. In Elias's era, the Earth still functions, but it has become smaller and dimmer. No crewed launches ever leave the atmosphere. For the children of the late 22nd century, the moon is an unreachable light, and the old dream of becoming a multiplanetary species has collapsed into mythology. The records Elias protects show a sky wrapped in a shell of abandoned upper stages, dead satellites, and metallic records moving faster than bullets. The connection to space was severed by the accumulation of our own debris. Elias faces a massive psychological barrier in our present day. When we look up, the sky looks empty. Rockets continue to reach orbit, and the danger remains abstract. To him, the satellite maps and real-time imagery we take for granted are ghosts, extinct wonders he has only ever seen in books. A spacefaring civilization enters its terminal phase through the slow, silent strangulation of its own future prospects. This 3D wireframe shows Earth surrounded by its distinct orbital shells. We are currently in Phase 1, saturation. Private companies and governments are filling these shells with tens of thousands of satellites in mega-constellations, mixed with decades of abandoned rocket boosters. The risk is driven by hypervelocity impact, a collision at such extreme speeds, often over 22,000 miles per hour, that kinetic energy vaporizes solid metal. At these speeds, a millimeter-sized paint fleck hits with the force of a bowling ball traveling at highway speeds. In Phase 2, the first fractures, a dead military satellite strikes a commercial platform. The impact creates hundreds of thousands of untrackable shrapnel pieces. These fragments immediately fan out, intersecting with the trajectories of every other object in that orbital lane. Despite the catastrophic physical reality in orbit, the reaction on the ground is brief. Markets dip for an afternoon and recover. Governments issue statements about orbital responsibility. The launches continue because the danger still feels like a manageable cost of doing business. This is the perspective of Dr. Mara Levin, a debris scientist who represents our current rational optimism. She views the growing wreckage as an incremental engineering challenge, something that can be addressed over time with better tracking and targeted cleanup missions. Human psychology handles linear growth well, but we struggle to grasp exponential physics. Treating orbital debris as a standard problem ignores the reality that the math can move past the point of no return while we are still debating the policy. This line graph maps debris volume of these three, the cascade years. For a decade, the growth appears manageable. Then it hits a mathematical inflection point where existing fragments collide to create new ones, triggering an unstoppable chain reaction. The effects multiply. Satellites burn through their fuel reserves to dodge incoming shrapnel. Insurance markets for space missions collapse. Entire orbital lanes become permanently unstable. Mara Levin's cleanup strategies fail against Elias's data. Levin assumes we can always send a machine to grab the largest pieces of trash. Elias knows that once the fragment density reaches a certain threshold, those cleanup machines are shredded before they can even reach their targets. This leads to Phase 4. The lock. Reaching a safe operational orbit becomes a game of Russian roulette. The sky is no longer a frontier. It is a minefield where the odds of a successful ascent drop with every passing month. Eventually, the attempts stop. Nations abandon spaceflight because the economic and political costs of a rocket failing to survive the ascent reach a breaking point. Humanity loses the stars to probability. We trap ourselves inside a lethal, impassable shell of our own making. Elias provides one final piece of evidence, archival records from the 2060s, documenting the last launch. The photograph shows a crowd watching a rocket ascend, their faces filled with grief. They are watching the final crewed mission leave Earth, knowing the corridor is closing behind them. Elias targets the specific moment before the first irreversible cascade threshold is crossed. He and Mara identify a cluster of abandoned, fuel-heavy upper stages from a defunct mega-constellation. If these objects collide, the resulting debris cloud will make future cleanup missions impossible. Neutralizing this single graveyard is the key to altering the timeline. This cascading destruction is called Kessler Syndrome. Kessler Syndrome is a scenario where the density of orbital objects is high enough that collisions create a self-sustaining cycle of new debris. The damage is cumulative, meaning the crisis remains hidden until it is too late to stop. Elias's arrival suggests a hard truth. A species must prove it can manage its shared frontiers before it can realistically hope to inhabit them. In the timeline where they succeed, humanity listens. Treaties are signed, dangerous objects are deorbited, and the cleanup era begins. Elias's doomed future is overwritten, replaced by a world where a child can look up at a launch and see a beginning rather than an ending. Engineering the rockets is only the first step. True civilizational maturity requires the discipline to solve invisible crises today, ensuring that tomorrow's generations are never cut off from their own horizon.